Okay, so my goal is to just go over different types of word problems that involve exponential functions and equations, since, you know, these are the ones that people tend to actually struggle with on the final exam. It does have a couple questions about solving exponential functions in word problem form. So I thought this would be a good thing to go over. Plus, then you can see how this stuff is used in real life. So there are basically, there's exponential growth and exponential decay when you have exponential functions. And so exponential growth, any questions that involve bacteria or viruses tend to be exponential growth problems. You've got anything with population, Moore's law, nuclear chain reactions are exponential, economic growth is usually exponential. And then we have compound interest, where you've got the compounded some amount of time per year, and then you've got continuous compound, which is with the E. And those are the ones that are most common on quizzes and stuff like that, the compound interest problems. And then exponential decay, anything like radiocarbon dating, half-life, atmospheric pressure actually has exponential decay when you model that. Newton's law of cooling, there's radioactive decay, which is very similar to radiocarbon dating. Beer, actually, the way that it disappears is exponential decay. And then for those in computer science, routing protocols actually involve exponential decay when you are trying to model routing and all that kind of stuff. But the common that you see in like algebra classes are the radiocarbon dating, Newton's law of cooling, half-life. Those types of problems are the most common that you see. So I'm starting out with the compound interest because these are the ones that show up on quizzes, exams, that sort of thing. So we've got a problem here. If a couple has $80,000 in a retirement account, how long will it take the money to grow to $1 million if it grows by 6% compounded continuously? So we have to use the formula for continuously compounding interest. So there are two different formulas, and when it says continuously, that is the formula A equals PE to the RT. So you have to look for that word. That's very important. And unfortunately, in real life, things do not compound continuously. So, or at least not as far as finances go, because that would be beneficial for us. And, banks don't like to do that because then they have to pay out more money. So they don't like to, it's in their best interest to do interest as little as possible. So we've got to identify what we have here. So P is always your starting amount. So they're starting with $80,000. So we're just going to label that. And then R is the interest rate. So that is 6%, which we use in decimal form. So you divide that by 100 to get the decimal form. And then we are looking for T because we want to know how long it will take to get to 1 million. So we're looking for when is it the amount going to equal to 1 million. So you identify all of your variables and your values, and then you plug them into your formula. So we have 1 million equals 80,000 e to the 0.06 t. Now, when I've got something with lots of zeros on the left and the right, you can cancel out, and this is just specifically for this type of equation, but you can basically cancel out zeros on the left and the right here because you're basically dividing by powers of 10. And so when you've got large numbers like this, it might be a lot easier to look at this without all of those zeros. So I can basically divide both sides by 10,000, which is canceling out 4 zeros. and we end up with 100 equals 8e to the 0.08t. And it's just easier to look at, especially when you're using things on your calculator. The biggest mistake I see people do is not have the right number of zeros when you're dealing with interest, because you want to have big numbers and stuff like that. So if you try to cancel out zeros like this, if you can, it just eliminates some of those potential problems of, miscounting your zeros, because that can, make a big difference in your answer. So we can basically cancel out zeros by dividing by 10 on both sides, and that allows us to cancel out 4 zeros. So we get 100 equals e to the, or equals 8e to the 0.08t. So when you're solving exponential equations, you have to divide both sides by the number in front of e before you can do anything else. So we're going to divide both sides by 8. And generally, when you have exponential problems, we tend to work with decimals instead of fractions. So this gives us 12.5 equals e to the 0.06t. So your goal is to get that exponential part by itself. So we have the e to the exponent part by itself. And when you get that, then you want to cancel out the e. You want to get your variable out of the exponent. So we have to reverse it or undo the e by taking the natural log, because the natural log is the inverse to Euler's number to e. So I always rewrite what I've got with the natural log there. I kind of write it in like this to say, or sometimes I try to squeeze it in just to kind of show that I'm doing the natural log, and I do it in a different color. But then I will actually rewrite it just so it looks nicer. And I always do my natural log in cursive, just because otherwise it looks like a 1n and it can get confusing. So I write it in cursive so that I know exactly what I've got. And so the natural log of e cancels out, and we have the rule of logarithms that says that your exponent basically ends up in front. So we end up with the natural log of 12.5 equals 0.06t. Now I try to round or wait to round to the very end, because if you round too early when you're solving, it can make a big difference in your answer. And then, when you're entering it into ALEKS, you're going to get the problem wrong, even if you did all the work correctly. So I don't actually calculate any of my natural logs until the end, just to avoid the rounding issues. If you do choose to calculate your natural logs before you get to the end, I would recommend using at least 5 decimal places, because that's usually enough to make sure that any rounding issues you might have don't show up. So we've got the natural log of 12.5 equals 0.06t, and I need to divide both sides by 0.06. And so this gives me t equals the natural log of 12.5 divided by 0.06. And then this is when I will actually do the natural log. And I usually try to do it all in my calculator at once. So in my calculator, I can do the natural log of 12.5 and my parentheses then divide by 0.06. So I'm going to just write out all of my decimal places here, because I want to make sure we're going to round correctly. Now, before I do the rounding, I have a question here. So for R and T, coming from the PE to the RT in the formula, they're both exponents. So when they come down, they get multiplied. That is correct. So in our formula, A equals PE to the RT, the R and the T are both exponents, and those are multiplied together. So when you take them out of the exponent, when you take the natural log, they're still multiplied together. So it's 0.06 times t. So that's why we divide both sides, since they are multiplied there. You're welcome. So yeah, I divided both sides by 0.06, and so we get this long decimal, and I always write down all of my decimals. We have 42.095477741. So it's telling us to round to the nearest year, which would be the nearest whole number. So we need to basically, I always draw a line where I want to round, and then I look at the digit after that line. If that number is below 5, then you don't have to do anything and you just keep what's to the left of the line. If the digit after the line is 5 or higher, you have to round up. So because this is 0, we don't need to round up. So we just keep everything to the left of the line, which is going to be 42. So it's going to be 42 years. And we always write our answer in a sentence, and you'll see this in Alex. They'll basically kind of usually will put it in words, and then you just plug in where the number is. But it will take 42 years, and we always include our units because units are important to know what you're counting in. 42 years for the account to reach $1 million. And that is a very long time. If you want to retire at 65 and you know it's taking 42 years, you need to put in that much money like immediately. And that's why, so this situation is if you put money in once and you never put any more money in it, and it just is only getting that interest, it will take 42 years. Now in real life, if you have a retirement account, you have money in it, and then you put more money in each year or whenever you get money, whenever you can afford to put more money in your account, you put more money in account. And so the formula for those kind of situations is a lot more complicated. That's something that you have to really look up because it gets way more complicated when you have to add in and you have more things going in. Yeah, the biggest thing is time. The difference of 10 years of compounding interest can be massive. Putting money in versus continually and letting it sit versus putting money in lots of times, that makes a big difference. I encourage you just to play around with the compound interest formulas. I actually have a spreadsheet where I have these interest formulas calculated in there, and Excel has the more complicated ones where if you you invest more money in it every year and things like that. But I use that to help decide where I'm going to put my money, where the biggest interest rate is going to make the biggest difference and stuff like that. So, but it's hard to make enough for retirement. I will tell you that. It's difficult. But that's a whole thing for economics and accounting. We're just focusing on the math here. We won't get into all the other nitty gritty stuff. Are there any questions on this problem? What symbol is the natural function on a calculator? That is an excellent question. So I'm going to briefly share my webcam, and hopefully this will show up on the webcam. So on my calculator, so this is what I've got. It's kind of blurry there. Okay, so on my calculator here, this is the natural log, ln. So it's in capital, which makes it a little bit easier. And then we've got the log button, but when you've got E, you want to use this one. Now, if you've got a graphing calculator, do I have one of those handy? I did at one point. Here we go. So I've got a graphing calculator here. This is the 89. So it is, let's see if I can get a little closer. Right here. Doesn't want to focus. you have to hit the second button and then get to natural log here. So it's a little bit harder in the graphing calculator. So I don't use this calculator to do my natural log stuff because it's more work. It's not a single button. I have to hit 2 buttons. And in Desmos, in the Desmos scientific calculator, there's a button as well. So good to know where those are. Okay, I'll get back to sharing my screen. All right. Get it to move on. Okay. Oh, there. Okay. Another compound interest problem. So we've got $20,000 invested at 3.5 interest, and this is compounded monthly. So this is how most savings accounts occur, is that you get your interest once a month. So it is compounded monthly. How long will it take from the investment to double? Round to the nearest tenth of a year. So this formula, we do not use E because it is monthly, which is N. And so N is 12 because there are 12 months in a year. So we're using the formula A equals P times 1 plus R over N, and then the exponent is N times T. So this is still the compound interest formula. It's just not continuous compounding. And so in this case, N is equal to 12. So there are basically 2 different ways to do this type of problem when it asks specifically for something to double. So we know that we are starting with $20,000. So P is 20,000. And we know R is 3.5%. So that's 0.035. So if we want the investment to double, then we want A to be $40,000. So you can do the math with P, plugging in 20,000, plugging in 40,000, and then plugging in your value for R. And of course, we have that N is equal to 12. Now, when you think about what it means to double, if we're starting with P, then doubling would be twice P, because double means you're multiplying by 2. So this double would be, your amount is twice times P. So if we look at our formula, I can put that into the formula. And you may notice that basically I can cancel out a P on both sides. And so this gives us a formula which is actually simpler. And what you will find is that if you want to know how long it will take for something to double, it doesn't matter how much you are starting with, because you see the principle that cancels out. It doesn't matter how long or how much you're starting with, it will take the same amount of time to double. If I had $10,000 at this interest rate versus $20,000 at this interest rate, they're both going to double in the same amount of time. It's a really interesting thing that you may not notice unless you are looking at what it means and you look at the formula. So you can solve your formula by plugging in $20,000, $40,000, or you can use what we have on the right, 2 equals 1 plus R over N to the N times T. So that's what I'm going to use. And if you solve using the 20,000 and 40,000, you will get to that same spot. But we're just kind of, it's like a slight little shortcut here. So we have 2 equals 1 plus r, which is 0.035 divided by 12. And then, oops, we know n is 12. And we're solving for t. We're solving for time. So I'm going to do the 1 plus 0.035 divided by 12 in my calculator. And you're going to get lots of decimal places. And so I just like to write down as many as I have, or like I said before, at least 5. But I just write down all of them just to be safe. So it actually will end up having a 6 repeating, but it rounds it up to 7 at the end. But that's what my calculator gave me. So we want to get the t out of the exponent. And so we've got 12 times t. We're not going to take the log of base 1.002916, whatever. That's just going to be gross. So we have 2 choices. We can take the log base 10 of both sides, or we can take the natural log on both sides. And it doesn't matter which one. You just have to do the same thing on both sides. I usually do the natural log because, well, we did the natural log on this one, and you know, we're solving it the same way. So I usually use natural log on both sides. Well, my calculator has a button for both, but that's usually what I end up doing. So we're going to take the natural log, and I'm just kind of squeezing that in. So we have the natural log of 2 equals the natural log. And let's say we do round this number to 5 decimal places just to be safe. 2, 3, 4, 5. So that would put my line between the 1 and the 6. And the 6 would cause us to round up so that 1 will become a 2. So if I round to 5 decimal places, I'd have 1.00292. Because 5 or higher after that line where we're rounding causes us to round up. So unlike with the natural log of e, this stuff doesn't cancel, so you still have that natural log there. But our exponent, everything in the exponent goes in front, and that's 12 times t, and then it's going to be multiplied by this natural log. So we have the natural log of 2 equals 12t times the natural log of 1.00292. And we're solving for t. So we're going to be dividing both sides, and I can divide both sides by 12 and the natural log of 1.00292. I can do those at the same time because they're all multiplied together. It's just a simple, just rearranging things. And I need to get rid of both of those. So I'm not actually taking my natural logs because I'm trying to avoid rounding as much as possible. So I do those natural logs last. So I have t equals the natural log of 2 divided by 12 times the natural log of 1.00292. And then you want to put this in your calculator. And if you put this in your calculator, you need to make sure that you have parentheses around your entire denominator, so to make sure that you're dividing by everything correctly. Because we're dividing by both the 12 and the natural log of 1.00292. So I make sure I put a parenthesis before my 12, and then I have my natural log 1.00292. I get 19.81046472. And if you have your own calculator handy, I would recommend doing this calculation on your calculator to make sure that you're doing it correctly. I typed it natural log of 2. I have my division symbol. Then I put a parenthesis, 12 times natural log of 1.00292. And then I closed my parenthesis to make sure that the denominator is taken together. So this problem says to round to the nearest tenth of a year. So tenth is 1 decimal place. So that's going to be after the 8. Now the number after the 8 is a 1. It's below 5, so we don't need to round up. So our answer is going to be 19.8. So it will take 19.8 years. Again, you want to include your units for the investment to double. Are there any questions? Okay. Now this one is a tricky one. Victor puts aside $10,000 in an account with interest compounded continuously, so we're back to E, at 2.7%. How long will it take him to earn $2,000? So when it says earn $2,000, that means how long will it take to become $12,000? Because if you're earning $2,000, you have added $2,000 on top of your original amount. Okay, question. The long decimals are a bit overwhelming. Did you say we should look at the first 5 digits? That is correct. If you stick with 5 digits after the decimal point and make sure you round those correctly, like I did at this point right here, you should be okay. So if you get overwhelmed with those long decimals, stick with 5. Okay, so back to this one here. Earning $2,000 does not mean when does the amount equal 2,000. It's 2,000 on top of your amount. So that's going to be 12,000 there. So that's something that it would be really easy to miss. And you would actually kind of figure it out if you solved it with your A equal 2,000, because the math wouldn't work out. You wouldn't end up with a negative number for time, because it's impossible to start with 10,000 and grow and get to 2,000, because that would actually be a decrease. So if you didn't notice or you didn't read this right and you used 2,000 for A, you would get a number for your time that was negative, and that would indicate to you, okay, something's not right here, because we can't have negative time. That would be time travel. So earning 2,000 is amount of $12,000. So we are using our formula A equals PE to the RT. So our starting amount is $10,000, so that's P. R is 2.7%, which is 0.027. And then we have A is 12,000. So I'm going to put this in the formula. 12,000 equals 10,000 e to the 0.027 t. And so I'm going to start canceling out zeros like I did in that first example, just so that I have some smaller numbers to work with. So I can cancel out 3 zeros on both sides. And so that gives us 12 equals 10 e to the 0.027 t. So I'm going to divide both sides by 10 so that I can get the e part by itself. And so that gives us 1.2 equals e to the 0.027 t. So we've got e, so we're going to do the natural log. So you take the natural log of both sides. So I'm going to have the natural log of 1.2 equals the natural log of e to the 0.027 t. And our rules say that the natural log of e cancels, and our exponent would be in front there. And so this gives us the natural log of 1.2 equals 0.027 t. So we divide both sides by 0.027. And so t is the natural log of 1.2 over 0.027. So I'm going to put this in my calculator. And I like to do it all in one step. Make sure that if you have parentheses for the around the 1.2, you close it before you hit the division symbol. And you should get 6.752650252. And it says to round to the nearest month. So what we have here is years. So our compound interest formulas are always giving you time in years. So this is about 6.75 years. But we want to round to the nearest month. So we're going to just kind of look at the 0.75 here. So that's 3/4 of a year, which has 12 months. So if you multiply 12 by 0.75, and I chose 0.75 because I know that it's a nice fraction. That's why I rounded it to that versus like 8. That gives you 9. So that would be 9 months. So our answer here is that it will take 6 years, because that's the whole number part, and 9 months to earn $2,000. So when you have a problem like this, it says round to the nearest month. Your other option, you can split it up like this, 6 years and 9 months, or if you don't want to do it this way, and I'm going to do this in, you could do 6.75 times 12, take that whole number wherever you've rounded it, and that would give you 81 months. So instead of saying 6 years and 9 months, you could say it will take 81 months to earn $2,000. So those are both rounding to the nearest month because they're both giving you the decimal part in months, essentially. One of them is giving you only the leftovers in months. The other one is giving you all of the numbers in months. Now, I think the first one that I did, 6 years and 9 months, kind of makes it's easier for us to understand than if somebody said it will take 81 months, because then you're like, well, how long is that? You know, you'd have to kind of do some math there. Are there any questions? All right. So if you don't get a nice decimal at the end, like a 0.25 or a 0.50, use the second method? Yes. That is an excellent question, John. Yeah. The 0.75, that, you know, we can round that nicely to a nice decimal, and that gave us 9 months. But yeah, if you got something weird, like if it was 6.4, still kind of a weird, you know, I would just do the second method and multiply it by 12 and then round to the nearest whole number. So that's an excellent question. All right, so now we're moving out of the compound interest into more the decay type of problems. So this is a half-life problem, and I like this problem because after I found this one in the book, I was like, you know what? I think I'm going to do this own calculation for myself to see how much how much caffeine is in my system when I go to bed. You know, from when the last time I stopped drinking coffee for the day. So I'm actually going to do this one on my own now that I have the right formula. But the problem is, so we've got the biological half-life of caffeine is approximately 6 hours. So that means you get half amount. It takes 6 hours for the amount to cut in half. Your friend was just talking about how much coffee he drinks. See, now you can actually do the math and figure out how much caffeine is in his system. So if 1 cup of coffee has 80 milligrams of caffeine, then the amount of caffeine, which we're going to use for C in milligrams, remaining after T hours is given by this formula. So we've got C equals 80 times 2 to the negative T divided by 6. So half-life formulas in the exponent, they divide by the half-life. And then they use 2 because you're dividing it by 2. So that's why 2 is like the base underneath there. So since it takes 6 hours for it to be cut in half, that's why we're dividing by 6. So we've got 2 problems here. On the left, how long would it take for the amount of caffeine to drop below 60 milligrams? So this one, all we need to do is replace C with 60. So, and it says how much it would take to get below 60. We're going to just do equal to 60 right now, and then we can, you know, write our sentence. So we've got 60 equals 80 times 2 to the negative T divided by 6. So first thing we're going to do is divide by 80. Do not multiply 80 times 2 because that 2 has an exponent on it, so they can't get multiplied. So you have to divide by 80 first. And so that's actually, that's should be 3/4 if I'm doing that mentally correctly. Yep, so that's 0.75 equals 2 to the negative T divided by 6. So just like with the compound interest formulas, I always just do the natural log because it doesn't matter, and so you could just use the natural log every time. So I just always do the natural log. So I'm going to do the natural log on both sides. So the natural log of 0.75 equals the natural log of 2 to the negative T divided by 6. And so our exponent here ends up being in front. So we've got the natural log of 0.75 equals negative t over 6 times the natural log of 2. So we're trying to get t by itself. And I'm actually going to multiply both sides by negative 6. Well, I'm going to multiply both sides by 6 to get rid of that 6 in the bottom. And I'm going to multiply by negative because I have a negative in front of it. So I'm just kind of squeezing those in. Why do the exponents keep dropping down? That is a property out of logarithms. Natural log, log base 10, any logarithm. Any exponent can be put in front of the natural log. I forget the name of the property. I might just be called the power property. But any exponents, when you have exponent on a natural log, it goes down in front. It's a good question. Okay, so I'm kind of squeezing in my work here. I've got negative 6 times the natural log of 0.75. And then that gives me t times the natural log of 2. So I multiplied both sides by negative 6 to get rid of the negative in the negative t over 6 part and to get rid of the 6 in the denominator. And so now I'm going to divide both sides by the natural log of 2. So I get t equals negative 6 natural log of 0.75. And then I'm running out of room, so I'm going to just write it like that, divided by the natural log of 2. And then I'm going to put this on in my calculator. And this comes out to 2.49022249996. And now the units here are in hours because the half-life is given in hours. So this is about 2.5 hours. It says to round to 1 decimal place. And so that 9 causes the 4 to round up. So it's about 2.5 hours. So that's how long it will take for the caffeine to drop below 60 milligrams. So then we've got a follow-up question. Laura has trouble sleeping if she has more than 30 milligrams of caffeine in her bloodstream. How many hours after drinking a cup of coffee would Laura have to wait so that the coffee would not disrupt her sleep? Around to 1 decimal place. So I'm interested in this problem particularly because I know people that say I don't drink any coffee after noon. I'm the type of person that I will drink coffee in the afternoon, assuming that I can still, if it's not too late, if it's not an evening, it's not going to disrupt my sleep. So now I'm curious, how many hours, how many hours do I actually need to wait? So this is basically the same type of problem we just did on the left, but instead of 60, it's now going to be 30. So what I'd like you guys to do, because I want you to kind of practice this as well, is I want you guys to do this on your piece of paper, and I will also do it on the screen, but I'm not going to say it out loud because I want you guys to try to work it out and then see if you get the same answer that I did, because I want to make sure that you guys can, do the steps. But the steps are basically going to be exactly the same here, just it's equal to 30 instead of 60. So I will let you guys do that, and I am going to just show all of my work here. And then when you get your answer, you could just type it in the chat box. So, and if you get stuck, you can always look on the screen to see where I'm at and see where where you missed. I'm actually running out of room, so I'm going to finish mine on the next slide. Okay, so you should get a positive value. Oops. Yeah, you should get a positive value. Let me just double check that I included my negative. Yep. So, because when you take the natural log of 0.375, that should give you a negative. So your two negatives should cancel. You should get a positive 8.49. And then depending on rounding, I got 0.224996. If you get 8.49019, that's okay, because if you round it to like one decimal place, they round the same. And so what I was going to then write is, so let's say your bedtime is 10 p.m. because basically it's going to take 8.5 hours, which is longer than I expected. So if bedtime is 8 p.m., stop drinking coffee. You got to work 8.5 hours. So 8, that would be 2 by 1:30, which is a lot earlier than I stopped drinking coffee. So I should probably stop drinking my coffee sooner. So the question didn't ask, when to stop drinking coffee. It just says, how many hours will she have to wait so that it doesn't disrupt her sleep. And so when you solve, you get 8.5 hours. So I just picked a hypothetical bedtime at 10 p.m. That then if that's, if that's how your body is, then stop drinking coffee by 1:30 p.m. And then, yes, try not to have a soda with dinner, because I think most pop actually has more caffeine than coffee. So it can really disrupt your sleep. So yeah, this was enlightening for me, because I had coffee at, I think it was at 4:30 this afternoon. So this could be why I'm so peppy right now. Um, yeah, so it takes about 8.5 hours for it to get down to 30 milligrams. Are there any questions?
Can you go back to the slide before really quick?
Yes, of course. I can get it to go. There we go. Yeah. I tried to do it in 2 different colors so that way you wouldn't get confused between the 2 different problems. Now this is interesting. So this is just for 1 cup of coffee. So if you have multiple cups of coffee like I do, you have to like do multiple equations for each cup, because it's kind of adding up. Like if I have 1 cup of coffee, or I start drinking it at like 8:30 in the morning, and then I have another one at 9:30 in the morning, the first one, that caffeine hasn't worn off yet. So now I've got the caffeine from the first one plus the caffeine from the new cup of coffee. So it would be really interesting to just, put this equation in an Excel spreadsheet and do it per time and figure out how much caffeine you have and how it accumulates.
Thank you. I'm finished.
Yeah, I'll go back just in case you need to do the second part as well.
Oh no, I did that part. Thank you.
Are there any other questions? I have more examples, but I know they're going to take, actually, I think we could probably squeeze this example in. So we'll do one more example here. A pie comes out of the oven at 325 degrees Fahrenheit and is placed to cool in a 70-degree Fahrenheit kitchen. The temperature of the pie in Fahrenheit after T minutes. So we got capital T and lowercase t. So capital T is temperature, lowercase t is time. Is given by T equals 70. So 70 is your starting, the temperature in the environment, plus 255 E to the negative 0.017 T. Now the 255 is the difference between the 325 and the 70. What we're using here is Newton's law of cooling, which is on this slide to get this formula. So this is an actual formula. This formula is actually how they use to, really morbid, but I'm a true crime fan, and they use this formula to calculate how long a body's been where it's been after it died. So, if you're in true crime, you've ever wondered how they know how long the body's been there, this is the formula that they use. But you can also use it here for food. So the pie is cool enough to cut when the temperature reaches 110 degrees. How long will this take? Round to the nearest minute. So we are going to use this formula to determine how long we need to let the pie sit before we cut it. Fun fact, one Thanksgiving I used this formula to figure out how long we needed to cook our turkey for. Because that's what a math person does. So we have our big temperature at 110 because we want to know when is this going to get down to 110. So I'm going to set that equal to capital T, and then we are solving for little t. So this to solve this, it's slightly different because we have to subtract 70 from both sides first before we do our dividing. So we need to subtract 70 from 110, which is 40. And then we can get to the point where we divide both sides. So I have 40 equals 255 e to the negative 0.017 t. And we're going to divide both sides by 255. Okay, that's giving me a gross decimal. So if you get lots of decimal places, good rule is to use 5 of them and make sure you're rounding correctly. So that would be 0.15686 equals e to the negative 0.017 t. So now I'm going to take the natural log of both sides so that I can cancel out the e part. So the natural log of 0.15686 equals the natural log of e to the negative 0.017 t. And our exponent has that property that it can drop down, and then the natural log of e cancels out. So we've got the natural log of 0.15686 equals negative 0.017 t. So we need to divide both sides by negative 0.017. And I'm going to go to my next slide to rewrite this. 0.15686 is negative 0.017 t. Make sure I'm properly dividing both sides by, do I have the correct number of zeros? That's the other thing. Make sure you have the right number of zeros. So t is equal to the natural log of 0.15686 divided by negative 0.017. Let me just double check that all my numbers are right. Yep. And so now we're going to put this in our calculator. And make sure that you type it in correctly. I accidentally put in an extra 0, so you don't want to do that. Okay. This gives us 108.96479995. So we need to know what are our units for t here. And it says in the problem that it is t minutes. So this is in minutes. So it says to round to the nearest minute. So that would be, if this is already in minutes, we're rounding to the nearest whole number. So that 9 will cause the 8 to be increased. And so we're going to round this to 109 minutes. So it will take 109 minutes for the pie to cool. Which is a long time. That's more than an hour and a half. That's a lot longer than I would have expected for a pie. But I imagine that it's insulated. It keeps the stuff inside, stays hot for a long time. So are there any questions on this problem?
I'm sorry, can you go back one more time?
Sure. If you're wondering, I explained where the 70 comes from in the formula, the 255. That value in front of the t, the negative 0.017, that is a value that if you were to use this equation in real life, you would have to figure it out based off of data. Like you would have to find two ordered pairs, like measure the temperature of the thing as it cools at two different times, and then put it into the equation, and you would be basically solving for R. In this case, it's given to us, so you don't have to do that math. But if you were to do that, like when I was doing this for how long the turkey needed to cook, I didn't know that number, so I had to take the temperature of the turkey at various times to find that number, so then I could figure out when it should be up to temperature, which you got to take the temperature of the turkey anyway to make sure it's cooked. So it was like I was already getting that data. Are there questions on any of the work? Okay. Well, this is, this is the last live. Let me stop sharing so you can see my face. So course ends Tuesday. The final exam is 2 hours, 15 minutes. And you want to have time after the final to submit your work. So I recommend giving yourself at least 3 hours of time before the course ends to make sure that you have enough time to do the final exam and then turn in all of the work. So course will close at 11:59 p.m. Central Time. So if you live in a different time zone, you're going to have to do some time conversions to make sure you have enough time. Because at 11:59 p.m., if you're in the middle of a final exam, it will just submit on you. Everything will just automatically submit at that deadline. So and then you won't be able to submit any work afterwards because the course will close to you. You will lose your access on that deadline. So just keep that in mind. Make sure that you start everything early enough so that you don't run into that problem. And the final exam is, I believe it's 10% of your grade. So you do not want to skip it. I've seen a lot of people who, for whatever reason, skip the final, which is not a good thing to do. So don't skip the final exam. Even if you don't think you're ready, it's better to take it than to get a 0. So should you be looking at previous quizzes for the final? Yes. So the final should be on weeks 5, 6, 7, and 8. And it will reuse questions from previous quizzes. So I would definitely study your previous quizzes. Any problems you got wrong on the quizzes, I would make sure you know how to do so that you get them right on the final if they show up. It will be pulling questions from the homework from week 8. You may see questions from the homework in weeks 5, 6, and 7 as well. That's where it should be pulling from. There are some questions that pull from like examples in the textbook. So if you're looking for something else to study, those are good to study as well. Other questions about the final? I think that's the most important things that you need to know. It is open book and open notes, of course. It is timed though, so that's why you got to make sure you have enough time. Okay. Well, if any of you guys are taking pre-calculus starting Wednesday, because we don't have a break between terms this time around, I am teaching pre-calculus. So I'll be your teacher if you're going on to pre-calc. So I may see you again. Otherwise, if this is your last math class, which I think for a lot of people it is, I'm sure you're pretty happy if most people are. So thanks for, yeah, I'm glad that you guys have been coming to live sessions and interacting. I really appreciate it. It makes it fun for me. And I wish you guys luck, your future classes, making sure you get to graduation and everything like that. It's been fun times. So everybody take care. Bye.